Thank you for the opportunity to speak to all of you. I'm sorry I couldn't be there in person. I've never been to India and would love to visit sometime, so hopefully soon. And from what I understand, the topic of this week's talks concerns the polynomial method in harmonic analysis. And that's going to be a theme for what I'm going to discuss today. I'll be discussing some results regarding maximal functions, which are a classic topic in harmonic analysis. And some of the proofs are going to involve the use of the polynomial method. So we'll see that a little bit later. Let's see if I can, one moment, can I switch? There we are. So the starting point for understanding maximal functions, everything I'm going to say is going to be in the plane, and maybe the prototypical maximal function is the Kakeya maximal function. So the setting is I have a function f from R2 to C, although for what we're considering, we can imagine it's from R2 to R and maybe even takes positive values. And for every direction E, so E can be a unit vector, what I'm going to do is I'm going to take the supremum over all unit line segments parallel to E. So I don't get to change, once E is fixed, I don't get to change the direction of L, but I can translate it around. And I'm going to slightly thicken it. So delta is a small number, and I'm going to take the delta neighborhood of L. So you should think of this as a rectangle, which has length 1 and width delta. And I'm going to average F over that rectangle. Whoops, I missed a symbol there. So I should have a 1 over delta involved because the area of the delta neighborhood of L is roughly delta. And so I'm going to divide by that area. And so I'm trying to find the largest possible average of F over any possible rectangle whose orientation is in the direction E. So for each unit vector E, this is going to be some, the supremum will be realized. It'll be, well, at least if F is an LP, and it'll be some well-defined real number. And you can ask, what are the LP mapping properties of this operator? And Cordoba, back in 1977, proved that this operator is almost bounded as a map from L2 to L2. So as delta goes to 0, the operator norm does go to infinity, but it grows in a fairly mild way. It grows like the square root of log of 1 over delta. And in this talk, that kind of growth, which is slower than any polynomial in 1 over delta, I'm going to suppress with this double squiggle notation. So there's a few reasons why this maximal function was of interest. So first of all, I'll mention that the largest possible LP norm for which you can hope to bound an operator, what do I want to say, the largest possible? Yes, the largest possible LP norm for which you can hope to bound an operator like this is L2. Make sure what I say what I want to say here. No, sorry. This is trivially bounded from L infinity to L infinity. So the smallest possible LP norm for which you can hope to bound this operator is L2. And you can see this by taking a focusing example where F is just the delta neighborhood of a ball. And on the other hand, you could ask, do we really need the operator norm to grow, to go to infinity as delta goes to 0? And it turns out, indeed, this must happen in some fashion because of the existence of measure zero Bezukovich sets. So these are these rather strange, some might say pathological objects. So there exist compact sets in the plane that have measure 0, but which contain a unit line segment pointing in every direction. And so if you thicken one of these very slightly, you take its delta neighborhood, you're going to get a set in the plane, which will have positive measure, but very small measure. Its measure will go to 0 as delta goes to 0. But this set will contain the delta neighborhood of a unit line segment in every direction. So in particular, the Kakeya maximal function, K delta F, if F is the characteristic function of such a set, will be 1 for every direction E. But F is a characteristic function of a set of very small measure. And so the only way you can hope to have an inequality like Cordoba's is if there's some sort of growth in the operator norm. So that's the setting for the types of geometric maximal functions in the plane that I'm going to be talking about. And the Kakeya maximal function is just one of many examples. So another fairly well understood example is called the Wolf circular maximal function. So this was studied by Tom Wolf in the 90s. And instead of fixing a direction E and taking the supremum over all lines pointing in the direction E, I'm going to fix a radius R, which I can think of as being between 1 and 2, let's say. And I'm going to take the supremum over all centers I'm going to look at the circle centered at x comma y of radius r. I'm going to thicken it very slightly. I'm going to take its delta neighborhood to create an annulus. And I'm going to average my function f over such an annulus. And so I think of the radius as being fixed, and then I get to move the center around to maximize this average. And the question is, how large can this be? And what Wolf proved is that this is bounded from L3 to L3. Well, not quite. As delta goes to 0, the operator norm, as a map from L3 to L3, does blow up, but in this subpolynomial way. And again, p equals 3 is the best possible, so the smallest possible value of p, for which you can hope for an inequality of this form. And there's a similar flavor of example called a Knapp example, where f is the characteristic function of a rectangle of dimensions 1 by the square root of delta. And again, the operator norm definitely blows up as delta goes to 0 because there are analogs of Bezukovich sets. They're called Bezukovich-Radon-Kinney sets. So these are sets that compact sets in the plane of measure 0, which contain a circle of every radius. So the situation with the Wolf circular maximal function is somewhat analogous to the Kakeya maximal function. There is another flavor of maximal function, which is sometimes called the Bourgain circular maximal function. Some of you might be more familiar with this one. And so there's two of them I've written here, but the idea is the same, where we're again averaging over circles, but instead of fixing a radius and taking a maximal average over all possible centers, instead I fix the center xy, and I'm taking a maximal average over all possible radii. So that's a slightly different setup. And you can either take a maximal average over the delta neighborhood of a circle, or you can try taking the maximal average over the circle itself. And in contrast to the situation with the Kakeya or Wolf maximal functions, the Bourgain maximal function actually is bounded as a map from LP to LP. And if P is bigger than 2, you can bound this with an operator norm that is independent of delta, from which you can recover this bound on BF as opposed to B sub delta F. And so that's a new phenomena. And a consequence of that is you don't see these sorts of measure 0 Kakeya-like sets or Bezukovich-Radon-Kinney type sets. So if you have a set in the plane which contains a circle with every center, or with every center in some set of positive measure, then that set can't possibly have measure 0. So they don't look like Bezukovich-Radon-Kinney sets. So there's really a qualitatively different behavior there. So these are the sorts of maximal functions we're interested in. They're fairly well understood at this point, at least these examples are. But I'll give one more example that we don't understand nearly as well. So this is called the elliptic maximal function. It was proposed by Erdogan, and it's similar to the Bourgain circular maximal function. So you should compare it to what you have on the bottom left screen, except instead of taking a supremum, so you fix xy, just as with the Bourgain circular maximal function, but instead of taking a supremum over all circles centered at xy, so you're taking a supremum over all possible radii, you're instead taking a less restricted supremum. So we're considering the supremum over all ellipses, which are centered at xy, but they can have major and minor axes, which are allowed to differ from each other. They can be, let's say, anywhere between 1/2 and 2. The major and minor axes don't need to agree. And then also you can rotate these ellipses by any angle theta between, say, 0 and 2 pi. So just to get a sense of what's going on, there is a 2-dimensional or a 2-parameter family of lines in the plane, which leads to what's effectively a 2-parameter family of line segments. In general, it takes 4 parameters to define a line segment, but for these sorts of questions, it's really the underlying lines that matter. So it's a 2-parameter family of lines. Circles are described by 3 parameters. You could think of it as the center and the radius. Ellipses are described by 5 parameters. You could think of it as the center, which is 2 parameters, the major and minor axes, which is another 2 parameters, and then the rotation. So that's a total of 5. So this is a more complicated maximal function. And correspondingly, if this thing is bounded in LP, you would expect it to be bounded for a larger value of P. And Erdogan conjectured it should be bounded for P bigger than 4. This conjecture is open, but there is some partial work in this direction of Li, and O, I believe, who proved that this is bounded when P is bigger than 12. So that's some progress in this direction. P equals infinity is fairly straightforward, and getting any finite P is not so obvious. Okay, so maybe a question I could ask you, I don't know how easy it is for people to respond to questions. So we'll see if this is possible with the technology. But a question I could ask you is, given all these maximal functions I've shown you, and these are all in the plane and they're all some sort of maximal average over curves, I could ask, if we were to generalize this idea and try to talk about maximal functions in general, what might the setup be? Like, what would be sort of the overarching theme of what I've shown so far? So I don't know if it's easy for someone to propose a suggestion and actually have me hear it. Is that possible? If somebody speaks, will I hear it, or does that not work?
Please repeat the question.
So the first question is it possible for people in the audience to talk and have me hear them?
Yes.
Great. And then the question I have for the audience is, if anyone is feeling bold and would like to propose, I've shown all these different maximal functions, averages over lines, over circles, over ellipses. Either you fix the radius or you fix the center. And so if I were to then ask, what is, in general, how might one talk about maximal functions? Like, what would be the generalization of these ideas? If I were to talk about the boundedness of a maximal function associated to curves, what might the setup be?
Well, for example, let's take the finite part of the parabola, take delta neighborhoods maybe.
Yeah, that's a great idea. Yeah, so that's another example of a maximal function. And we could try to ask, can we define in a general sense what a maximal function might look like? And so one possible way to do that, to set things up, is we could talk about a family of curves. And one way to talk about a family of curves is we could say, well, I have some manifold, which I'll call C, and I have an interval. And I'm going to think of my curves as being, so what I've written here is gamma sub W. So these are going to be the graph T comma H of omega T, where T is in this interval and omega is a point in my manifold. So you can think of H as being some sort of function that parameterizes the various curves in my family of curves. So I'll come to some examples in a moment, but this is a definition which is trying to capture circles, or at least pieces of circles, line segments, ellipses, and so on. And in order to be able to say something in this setup, I want to talk about how tangent curves can be to each other. So distinct lines can't be tangent at all. They can intersect, which you can call being tangent to 0th order, but they can't be tangent. Circles, distinct circles can be tangent to each other. You could say tangent to 1st order, but they can't be tangent to 2nd order. Like if two circles are tangent and their curvatures match, then they're the same circle. Ellipses, on the other hand, they can be tangent to 1st order. Their curvature can agree, which you can think of as being tangent to 2nd order. They can even be tangent to 3rd order and still be distinct. But the moment they're tangent to 4th order, then the ellipses have to coincide. So how can we try to make that idea precise? Well, there's a slightly technical condition. So if you fix some point t or some time t in your interval, then for each curve omega, you can ask where is this curve at time t? So what is h of omega t? And also what is the slope of this curve? So that's the derivative with respect to t of h of omega t. And you could ask what is the 2nd derivative, the 3rd derivative, so on and so forth, all the way up to the m minus 1st derivative. And what I'd like to say is if you know all that information, then that uniquely determines what the curve is, which is the same as saying, if you know for lines, if you fix a point and you fix a slope, then you know what the line is. There's a unique line passing through that point, having that slope. For circles, if you fix a point, fix a slope, and then fix a 2nd derivative, there's only one circle which passes through that point and has the prescribed slope and 2nd derivative at that point. For ellipses, you have to fix a point, fix the 1st derivative, 2nd derivative, 3rd derivative, 4th derivative, and then after you fix all that, you know what the ellipse is. So this is saying that this map from the set of curves to Rm is a local diffeomorphism, or you could even ask that it's a global diffeomorphism, right? So once you know that information at some fixed point t, then you know what the curve is. So this is a setup which can be used to generalize all these maximal functions I've described to you. And we're also going to need this notion of a projection. So For the Kakeya maximal function, for each direction, we pick one line pointing in that direction. So you can imagine mapping a line to its direction. Or in the Wolf maximal function, for each radius, we pick a circle of that radius. So you can imagine mapping a circle to its radius, or for the Bourgain circular maximal function, for each center, we pick a circle with that center. So you could imagine mapping the point, the circle center to xy of radius r to x comma y. And so in general, we can talk about a projection in this way. And we're going to impose a slightly technical condition, which says that this projection is transverse to the function defining my curves. And I won't go into too much detail saying what that means, but what this is saying is if you fix some curve, so omega in c, and you fix some time t, then you can look at this projection function and you can look at its derivative, and you want that to have full rank when it's restricted to a certain submanifold of C. And what is the submanifold? It's the set of curves which at time t agree with your curve omega up to the m minus dth derivative. And I won't talk too much about this condition, but somehow this is a natural condition to impose to have your function phi generalize this notion of taking a circle to its center or taking a circle to its radius or a line to its direction. Okay, so why have we set up this family of curves C and this projection function phi? Well, it's because now we can define a maximal function. So for every v in the image of phi, I can define m sub delta f of v. And this is the average over the delta neighborhood of all curves whose projection is v. And I can also define a version without the deltas, where instead of taking the average over the delta neighborhood, I just take an average over the curve itself. So hopefully this definition makes sense, but let's look at a few examples just to get a sense of what's going on. So the whole point is that all the examples we started with of different maximal functions can be expressed in this way. So the Kakeya maximal function, our manifold of curves is just R2. And what is our function h? Well, if you give me a slope m and a y-intercept b, then at time t, my function is equal to m times t plus b, right? Slope times t plus y-intercept. And what is my projection function? Well, it takes a slope and a y-intercept, and it just gives you back the slope, right? This is the same as the direction of the line. So that's just the Kakeya maximal function in this language. And the Wolf maximal function, also not too bad. So centers can be in R2, so that's x comma y. And whoops, there's a typo there. What I wrote as 0, 1 should be 1 comma 2. I want the radius to be between 1 and 2, not between 0 and 1. So apologies for that. And what is my function? You give me a point x comma y and a radius r, and then I'm just parameterizing the upper half of the circle center to x, y of radius r. And hopefully I wrote that down correctly. And what is my projection function? Well, given a circle center to x, y of radius r, I'm just giving you back the radius. And so with this choice of h and this choice of phi, the maximal function defined in the bottom right is just the Wolf circular maximal function. Well, okay, not quite. It's not the average over the entire circle. It's only the average over a half semicircle, but that's not a big deal. The Bourgain circular maximal function is defined, same idea. All you do is you change the defining function phi. Instead of phi of x, y, r being r, it's just x comma y. And finally, the elliptic maximal operator is a little more complicated because what's the manifold? Well, it's the set of possible centers, x, y, and major and minor axes between 1/2 and 2, and rotations theta. And then what is h of x, y, a, b, theta? Well, you're parameterizing, say, the upper half of the ellipse centered at x, y of major axis a, minor axis b, rotation theta. So it's a more complicated formula, but it's sort of similar to square root of r squared minus t minus x squared minus y. It's just the more complicated formula that parameterizes an ellipse. So all these maximal functions fit into this kind of framework. And the point is that we can prove theorems about maximal functions in this kind of framework. So if you have any maximal function, m sub delta, defined as we've discussed, then this is going to be bounded, well, almost. There'll be this slow growth in the operator norm from LP to LP. And what is the value of P? Well, it's exactly the value which matches everything we've seen so far, including Erdogan's conjecture. So it's P equals m minus d plus 1. And what about the Bourgain circular maximal function, or the Erdogan one for that matter, because they're interested not in averaging not over the delta neighborhood of a curve, but over the curve itself. And so if your maximal operator is what's called translation invariant, then you can show that this thing is bounded from LP to LP for all P strictly bigger than M minus D plus 1, right? So the Bourgain maximal operator B sub F, that was bounded for P bigger than 2. The Erdogan one was conjectured to be bounded for P bigger than 4. And so that's the setting for item 2. So I won't tell you what it means for M to be translation invariant, but I'll say that the examples we've seen are of the Bourgain circular maximal operator, the elliptic maximal operator. These are translation invariant. So this result applies to that. And how does this corollary work? Well, you take the first bound, equation 1, and you interpolate this with what's called a local smoothing estimate. And the relevant local smoothing estimate for this problem is due to Chen, Guo, and Yang. It's a recent result of theirs. Xiaoming maybe was going to talk about this result. I'm not sure. You'll have to find another opportunity to hear him speak about it. But it's a very nice local smoothing result that they proved, which allows you to take estimates of the type equation 1 and turn them into estimates of the type equation 2, at least in the translation invariant setting. So this theorem, theorem 1, which implies its corollary, is the main result I want to talk about today. And I want to focus a bit on some of the ideas involved in the proof, which, as promised, are going to involve the polynomial method. So let's talk a little bit about some pieces of the proof. And I'm going to focus on the case D equals 1. So then M minus D plus 1 is just M. And in order to prove this inequality 1, there is an adjoint formulation, which I won't explain how you get from the original result to the adjoint result, but I'll just say it's essentially just the duality of little LP spaces. But this adjoint formulation on the bottom right, you can, if you want, forget everything I've said so far about the setup and look at this new setup, which is equivalent, but is written slightly differently. So here's our new setup. I have this interval I, same interval as before. And I have a finite set of curves, which I'll call capital F, and they're all smooth curves on this interval I. And this collection of curves has a sort of interesting property. So take any two curves, F and G, from my set capital F, and fix any time t in the interval I. And I'm going to look at the difference of F minus G evaluated at t, the absolute value of that, plus the absolute value of the difference of the derivatives, plus the absolute value of the difference of the second derivatives and third derivatives, so on and so forth, all the way to the m minus first derivatives. And I'd like to say that when you add all these together, they can't all be small if F and G are far apart in their m minus 1 smoothness norm. So certainly this f of t minus g of t plus f prime of t minus g prime of t, so on and so forth, this sum is bounded by a constant times the difference between f minus g in the cm minus 1 norm. That's more or less the supremum of this quantity, more or less, is the cm minus 1 norm of f minus g. But I want a reverse inequality for every time t. And so what does this mean? It's what it says is that distinct curves cannot be tangent to m minus first order. They can be tangent to m minus second order, but not to m minus first order, right? If two curves are tangent to m minus first order, then this entire quantity, f of t minus g of t, so on and so forth, would be 0, even though if the curves are distinct, then their cm minus 1 norms are not going to be the same. So it's very, very closely related to this, what I said earlier, where this function h is a local diffeomorphism. So it's more or less the same condition. So imagine I have some set capital F of curves with this property, and it's a finite set of curves. And how many are there? Well, I could imagine so delta is a small number, which I'm going to be interested in the asymptotics as delta goes to 0. And I could imagine that there's roughly 1 over delta of these curves. So capital F has size roughly 1 over delta, let's say. And they're not too concentrated in the metric space Cm minus 1. So sorry, that K should be should be M minus 1 there on the top left board. So if you were to take any ball of radius r in the Cm minus 1 norm and ask how many curves from F are inside of that ball, I want there to be at most r over delta. So sometimes this is called a one-dimensional Frostman condition on the set F. And this is very closely related to my projection function phi being smooth. So if I have a collection of curves with this property, then what I'm going to do is I'm going to take each curve, I'm going to take its graph, so that's now a subset of R2, or really it's the interval I cross R, and I'm going to take its delta neighborhood. So it's the thickened neighborhood of the graph of this function f. And I'm going to take the characteristic function of that, and I'm going to sum these for all the functions in f. And I want to understand the LP norm of the sum of these thickened characteristic functions. And I would like a bound. I want to say that up to factors that are sub-polynomial in delta, this looks like delta times the number of curves to the 1 over p. And so this is true if p is m over m minus 1, which is the dual exponent to m, which is the whole point, right? So equation 1 on the top right board, if d equals 1, then this is an LP bound for p equals m. The dual exponent is m over m minus 1. And so we've proved this adjoint formulation for the dual p prime exponent. So I claim if we can prove this inequality on the top left board, then it implies the main theorem in the case where p equals, in the case where d equals 1, so p equals m. And I won't talk about how to get from there to the general case, but it's not too hard. Okay, I'll pause for a moment and ask if there's any questions about what I've said so far.
Hello. No question, but we think that it might be good if we take a break at 45 minutes for like 5 minutes and then resume.
That's a great idea. Let's do that.
Thanks.
So I think we have 15 minutes before we hit 45, and we'll certainly take a break then.
Thanks.
So let's try to prove this result. And maybe a starting point is, well, I told you that m over m minus 1 is the dual exponent to m. So if we can prove this inequality 3, it implies inequality 1, which is good. But why would we hope for this to be true for p equals m over m minus 1? Where did that come from? And so one example to consider, so the bottom right board tells us that distinct curves are not allowed to be tangent to order m minus 1, but they are allowed to be tangent to order m minus 2. So for example, let's say we're dealing with circles. So for circles, m equals 3. So what that says is circles can be tangent to each other, but they're not allowed to be tangent to second order. So they're not allowed for distinct circles to be tangent and have their curvature agree, but they are allowed to be tangent. And distinct ellipses can actually be tangent to third order, but not to fourth order. So it could be the case that all the curves in my family are as tangent to the maximum allowable order, which would be m minus 2. And it would look something like this picture on the bottom left, which is called a clamshell. So all the curves are mutually tangent at a common point. And if the curves are all tangent, then what happens when you thicken them? So you look at their delta neighborhoods and you ask, how much do those delta neighborhoods overlap? Well, they're going to overlap in something which looks a bit like a rectangle. It might be a curved rectangle, but something kind of rectangular. And what are its dimensions? Well, in one direction, it's going to have thickness delta, because these are the delta neighborhoods of curves. In the other direction, it's going to have thickness delta to the 1 over m minus 1. So, for example, if circles of very distinct curvatures are tangent to each other and you thicken them by delta, then their delta neighborhoods intersect in a rectangle of dimensions delta by delta to the 1/2. And for these ellipses, if they're as tangent to each other as they're allowed to be, given that they're quite distinct, then they're going to intersect in a rectangle of dimensions delta times delta to the 1 over 4, which is a much larger rectangle. So if that were to happen, then this item in equation 3, the LP norm of the sum of the thickened characteristic functions of these curves, well, probably most of the contribution from the LP norm is going to come from where all these curves overlap with each other. At least that's a possibility we have to think about. So what is the area of this rectangle? It has dimensions delta times delta to the 1 over m minus 1. So its area is delta to the 1 plus 1 over m minus 1. What is this? How many functions are there? There's, well, the cardinality of capital F is a number of functions. And so that raised to the power of p, this expression on the upper right. Actually, as a quick question, if I move my cursor around, do you see it?
Yes.
Ah, great. Okay. Because I've been moving it around. It occurs to me maybe I'm just doing it for my own benefit. Great. So hopefully, as you can see with my moving cursor, this quantity on the upper right is just the contribution to the LP norm coming from this rectangle. And the theorem we're trying to prove says that this has size at most delta times the cardinality of f. And how big can f be? Well, the biggest it can be in cardinality is 1 over delta. And you compare all these facts together and you conclude that there's no way to prove inequality 3 unless p is less than or equal to m over m minus 1. And that corresponds in the dual setting. There's no way to prove what used to be called inequality 1 unless p is at least as big as m. So this is the m over m minus 1 is the smallest value of p for which you can hope to, what do I want to say? M over m minus 1 is the largest value of p for which you can hope to prove an inequality like this. And that's indeed the value of p for which we can achieve this inequality. And so let's now try to get an idea of how it's proved. And as a starting point, we could say, well, in this particular configuration, all the curves were mutually tangent to the highest possible order. They were allowed to be tangent, but they were all tangent at a single location, all in a single clamshell. And maybe if I'm more clever, I can arrange these curves so that maybe not all of them, but a lot of them are all tangent in one place to make a clamshell. But then maybe a lot of them are tangent in some other place to make another clamshell. Maybe the same curve can be reused many times to make many different clamshells. And if that were to happen, it could lead to a collection of curves for which the LP norm in equation 3 might be very large, so large that maybe equation 3 is wrong. I mean, that would conceivably be a way to create a counterexample to inequality 3. So imagine you have this collection of curves and they form some number of clamshells, which I'll call capital N. And how many curves contribute to each one of the clamshells? Well, maybe it's not all of them, which would be the cardinality of f. Maybe it's some slightly smaller number, so I'll call that mu. So imagine I have n different clamshells, and each of them have mu different curves contributing. So if that were to happen, I could ask, what does the LP norm look like for p equals m over m minus 1? And well, it's the number of clamshells times the area of each clamshell times mu to the m over m minus 1. And I want to compare that with what it's supposed to be, which is delta times the cardinality of f. And well, okay, can I create a counterexample? Well, if I can do this so that I get a large number of clamshells, if n is much larger than the cardinality of f over mu to the m over m minus 1, then I could indeed create a counterexample to inequality 3. So a question we can then ask is that possible? Is it possible to construct a configuration of curves, capital F, and pick some number mu so that we actually get such a large number of clamshells that it violates inequality 3? And I claim that more or less the only way inequality 3 can be violated is if we can construct a collection of curves which create clamshells in this way. And so the next result says, no, you can't do this. So with the definitions on the bottom right, where I have these clamshells, and I can ask how many clamshells are there allowed to be? Well, it's at most the size of f over mu to the m over m minus 1. So this is saying that the attempt to create a counterexample that we discussed in the bottom right is not going to succeed. Okay, so that's a little bit vague. Let's try to be a little bit more precise. So in order to be more precise, we need to talk about what a clamshell is, and we have to talk about what it means to be mu rich and things like that. So let's try to actually define that. And so let's fix some small number delta and an integer k. And I'm going to say that a delta k rectangle is going to be the delta neighborhood of the graph of a function whose ck norm is at most 1, let's say. And that's going to be the graph above an interval of length delta to the 1 over k. So I've drawn a little picture here of what that might look like. The interval I've called capital I. It has length delta to the 1 over k. In the middle is the graph of my function. And so this is the sort of set that I'm interested in. And these are the sorts of curvilinear rectangles which can be used to make clamshells. So that's a delta k rectangle. And I'm going to say that a function f is tangent to a rectangle r. I write that as f twiddle r. So r is a rectangle above some interval I. And if I take the graph of f and I restrict it to I, then if that graph is contained in R, then I say that f is tangent to R. So I've drawn a picture there where I have a rectangle R and I have this function f, I've drawn its graph. And if the graph, when I restrict to I, is contained in R, then I say you're tangent, otherwise you are not tangent. And I say that a rectangle is mu rich for some integer mu if, well, okay, so I have this collection capital F of functions. So to be mu rich is with respect to a collection of functions, capital F. So if there is at least mu functions in capital F, each of which is tangent to R, then I say that you're mu rich. So it's counting the richness of a rectangle is the number of functions that are tangent to it. And I say that a rectangle is narrow. So this is I drew some pictures here because the definition's a little bit technical, but let's imagine for the moment that I have a delta K rectangle, let's call it capital R, and I have two different functions, call them F and G, both of which are tangent to this rectangle R. And let's say F and G are both CK functions and their CK norm is at most 1. So what this means is that F and G almost agree with each other on a fairly long interval. So on an interval of length delta to the 1 over K, the difference between F and G is at most delta. And this tells me something about the higher order derivatives of F as well. If you were to pick a point in this interval, then F minus G at that point is going to have size at most delta. But the derivative of F minus G also can't be all that large. It can be at most delta to the 1 minus 1 over K. And the second derivative can be at most delta to the 1 minus 2 over K. And the third derivative delta to the 1 minus 3 over K, and so on and so forth. That's just an exercise using Taylor's theorem. So in particular, if I know that my functions are CK and their CK norm is at most 1, then if two functions are tangent to a common rectangle, then after they leave that rectangle, the functions can diverge from each other, but not all that quickly. Like if they've gone distance t away from the rectangle, then their difference can be on the order of t to the k, but not any more than that. And I say a rectangle is narrow if most of the curves that are tangent to R, as they leave R, they don't diverge as fast as they're allowed to, which would be t to the k. They kind of remain close for a while. And what this would mean is that there's some larger rectangle, which is much longer, which contains most of the curves tangent to R. So I've drawn this picture on the bottom right board where the dotted line denotes a much longer rectangle, which is a little bit bigger, but much, much longer. And all the curves that were tangent to R remain trapped in that rectangle. So that's maybe an unusual situation. It's saying that in some sense, I didn't pick the correct rectangle R. The one with the dotted lines is a more interesting rectangle. It more accurately captures the geometry of what's happening. So there's a technical definition, which I'm not going to give you, but is more or less what this picture says. So if this picture is not happening, then we say the rectangle is broad. If it is happening, we say it's narrow. And for those of you that are familiar with things like restriction problem in higher dimensions and multilinear Kikeya and things like this, this is very closely related to the broad-narrow dichotomy, which occurs there as well, even though everything is in the plane. Okay, so this is my definition of what it means to be broad. And so now we can actually state a more precise theorem, modulo the slightly vague definition of broadness. So let's say I have a collection of smooth functions on some interval, and I have a set of pairwise incomparable. Oh, did I say? Oh, yes. So I didn't tell you what it means for rectangles to be comparable. So two rectangles are comparable if one of them is contained in the twofold dilate of the other. If that doesn't happen, then they're incomparable. So what this theorem says is, let's say I have a finite set of smooth curves, and their CK norm is all at most 1, let's say. And I have a collection of pairwise incomparable rectangles. So no rectangle is contained in the twofold dilate of any of the others. So they're really distinct from each other in a meaningful way. And each one of these rectangles is mu rich with respect to F for some integer mu, and it's broad. And these are all delta K rectangles. Well, then I can give you a bound on how many rectangles there can be. It's the size of the set F divided by mu, all to the K plus 1 over K. So we were interested in the situation where K equals M minus 1. And in that case, the exponent would be M over M minus 1. But this is true for general K. So this is the precise version of that result I mentioned previously. And what this is telling us is that potential counterexample, which we saw a few minutes ago, in fact, can't exist. And I claim that counterexample was really the only enemy to proving this sort of LP bounds I was claiming earlier. So it, morally speaking, follows that this theorem on the top left implies the main theorem I was discussing before. In reality, a bit of work is required, but this is the main geometric input. So the proof of this theorem involves a number of ideas, but one of them is the polynomial method, which increasingly has been used in harmonic analysis. And so the second half of the talk will be devoted to giving some of the ideas of the proof of this theorem and seeing how the polynomial method plays a role. It's maybe not entirely obvious because everything we've done so far is involving smooth functions or functions of controlled CK norm. So we'll see where polynomials come into the picture. Okay, so let's break there because we're 45 minutes off the hour for 5 minutes.
May I ask a few questions?
Oh, yes, absolutely.
So a couple of things to prove that theorem. Do you think that it is sufficient to prove it for, let's say, the special class of curves, which are polynomials of degree up to m+1, little m+1?
Yeah, so let's be careful because let's say we just want to prove the result for circles, for example, or ellipses. The setup that I've described to you, I'm writing these functions as the graph, or I'm writing these curves as the graphs of functions. And so even a circle, which is a very simple object, if I want to write it as the graph of a function, that function is smooth, it's analytic in fact, but it's not going to be a polynomial. So we have to be a little bit careful. Does that answer your question?
Yes, but because we are looking at a delta neighborhood, right? So if we do, let's say, Taylor expansion around that point, which is basically saying broad rectangles, right? So the expectation is that even if we leave that rectangle, it shouldn't be too far, which is basically saying the Taylor polynomials of two functions should not be too far from each other, the m+1 derivative, if I understand correctly.
Okay, let me actually go back to sharing my screen so I can point at some things. So there's two objects floating around. There's the definition of a delta K rectangle. So that is the delta neighborhood of the graph of a CK function above an interval of length delta to the 1 over K. And for that, it would suffice to consider the delta neighborhood of the graph of a polynomial of degree at most K, because you can replace this function by its Taylor expansion to degree K, and the two coincide up to error delta, which is good enough. For the functions in capital F, however, while it is true that for any given rectangle, or on any given rectangle, the function is accurately approximated by its Taylor approximation, we're interested in this function over the entire interval I, which could have length on the order of 1. And in order to accurately approximate a function over an interval of length 1 to accuracy delta using a Taylor approximation, that's going to be a bit problematic. It is true that you can take a smooth function and actually, what do I want to say? There are approximation theorems which play a role here, which say that you can accurately approximate a smooth function to accuracy delta with a fairly low degree polynomial. It's going to have order on the 1 over delta to the epsilon, roughly, which is going to be good enough for what we're doing. So you can take relatively low degree polynomials, but relatively low means they go to infinity as delta goes to 0, but they go fairly slowly to infinity as delta goes to 0. I don't see any way to recover the main result if we're only considering polynomials of degree at most K, for example.
Hello, thanks. Joshua, if you are ready, we may start. I think it's been 5 minutes. Thanks.
Okay, very good. So just to recap, we began by discussing a collection of maximal functions. So the Kakea maximal function, the Wolf and Bourgain circular maximal functions, and the Erdogan elliptic maximal function. And then we came up with a general definition which captures all these maximal functions and stated a theorem about the operator norm LP to LP bounds of this collection of maximal functions. And we have reduced the question of obtaining those operator norm bounds to this geometric question. So you have a collection of smooth functions whose bounded CK norm, and you have a collection of rectangles, each of which are tangent to many of these functions, to mu of these functions. And these rectangles are broad, and we need to control the cardinality of such a collection. And we need this bound on the upper left board. The cardinality of R is at most the size of f over mu to the k plus 1 over k, where these are delta k rectangles. So there's definitely some work involved, but I claim if we can prove this inequality on the top left board, then that's the major difficulty in proving all the results we've discussed so far. So oops, let's make that work. There we are. So let's discuss some of the steps involved. And the first idea, well, I'm sure it goes back a long way, but I first became aware of it as an idea of Joseph Shalamoshi, and it appears in a paper by him, Jordan Ellenberg, and myself. And we began with these functions little f, which are in the set capital F, and take each function. You can write its graph. So that's a plane curve, t comma f of t. And I'm going to lift each one of these plane curves to a space curve, which I'm going to write as t comma f of t comma f prime of t, f double prime of t, all the way to the k minus first derivative of t. So this object it's a curve in rk plus 1. It's the graph of some function from r to rk. And so it's this higher order tangency lift. And I'm also going to take my delta k rectangles. So these are curvilinear rectangles in the plane, a bit like what's on the top right board. And I'm going to lift these to prisms, which I'll call r hat, in rk plus 1. And how am I going to do that? Well, each one of these prisms is the graph of some ck function above an interval of length delta to the 1 over k. And so I'm going to lift this to rk plus 1, where I still have some interval I. And then in the first coordinate, that's going to be the set of points whose distance from my function is at most delta. And then in the second coordinate, it's the set of points whose distance from the derivative is at most delta to the 1 minus 1 over k. And then in the third coordinate, it's the set of points whose distance to the second derivative is most delta to the 1 minus 2 over k, and so on and so forth. And why am I doing this? Well, if in the plane I had some function f, which was tangent to a rectangle r, then after I lift to rk plus 1, f hat is going to be tangent to r hat. And what do I mean by tangent in this setting, or incident in this setting? Is r was defined above some interval I. R tilde, that should still be an r hat on the top right board there. So apologies for that typo. So r hat is still going to be defined above this interval I. And so if I restrict the function f hat to this interval I, then it's going to be contained in r hat. So exactly the same type of thing. And this goes back to what we were discussing in the middle of the discussion of broadness, where if two functions are tangent to the same rectangle R, then this tells me something not only about how their values agree on R, but also gives me information about how their derivative and second derivative and third derivative and so on have to somewhat agree on R. And so this tangency lift is a way of capturing that geometrically. And so I'll say on the left picture that F is incident to R, or F is tangent to R, and on the right that F hat is incident to R hat. And again, that should be an R hat, not an R tilde. Okay, so hopefully that definition makes sense. And this theorem on the top left board then becomes more or less equivalent to this result on the top right board. So I take each of my curves in capital F and I take its lift. Oops, I see there's something in the chat. Let me check in there. Some suggestions about approximating polynomials. Thanks. I'll look into that. Circling back to what I was saying a moment ago. So I have my collection of functions capital F, and I can take the lift of each one. So for each little f, I take little f hat and call that collection capital F hat. So these are now space curves, or the functions whose graphs are space curves. And I had this collection of rectangles, and I'm going to take their lifts. So I get a collection of tangency prisms. And the number of tangency rectangles in my original collection is equal to the number of tangency prisms in my new collection. And I just want the same bound as before. But I'm going to be a little bit more precise about what that double squiggle means. It means that for any positive epsilon, I can bound it by, the way I've written this is this quantity to the power of epsilon, or maybe there's a constant depending on epsilon, or maybe as long as delta is sufficiently small, I can get an inequality of this form. So this is now what I'd like to prove, this upper right board. And how can we do this? Whoops, let me there we are. I'm going to just discuss the special case where mu, the richness, is on the order of 1. And I claim if you can prove this inequality when mu equals 1, then using ideas from what's called random sampling, you can prove the general case. So the general case of mu can be reduced to the case mu equals 1 by random sampling. So I won't talk about that. I'll say that the real geometric interest comes from the situation where mu is equal to 1. And in that setting, we're now going to use the polynomial method. So there was a bit of discussion during the break and just now that if you have a smooth function, then you can approximate it by a polynomial of moderately low degree up to accuracy delta. So if my function is C infinity and I have some control over its Cj norms, then if I'm trying to approximate this function up to error delta, I can do so with a polynomial whose degree is roughly 1 over delta to the epsilon times a constant, and that constant is going to depend on the ck norms of this function for k goes from 1 to 1 over epsilon. And so these are all going to be under control for what we're doing. So it more or less lets me go from a smooth function to a polynomial, and the degree of the polynomial is going to grow as delta goes to 0, but it's going to grow fairly slowly. So it'll grow more slowly than any polynomial in delta. And for everything I'm going to do, that's going to be acceptable. So I'm now going to make the jump from smooth curves to algebraic curves. And we do have to keep track of the degree of everything involved, but I'm just going to claim that these degrees are low enough, they don't cause any problems. But for any result, there does need to be a quantitative dependence on the degree. Okay, so here is this crucial theorem, which the first iteration of it appeared in Guth and Katz's seminal proof of the Erdős distinct distances conjecture in the plane. And there was a follow-up, slightly more general partitioning result by Guth a few years later, even though they both were published in the same year. And so this is often called polynomial partitioning. And a lot of modern results using the polynomial method start with polynomial partitioning. So here's the setup. I have a collection of algebraic curves in RD. I'll call that capital gamma, and they're all of controlled degree. And there is a parameter, capital E, that I get to choose. It's going to be a fairly large number, an integer. Then what this theorem says is there exists a polynomial P in D variables, because we're in RD, and the degree is at most capital E. So I get to choose the degree. And it has this interesting property that, so the 0 set of P is going to be closed. It's an algebraic variety. And the complement of the 0 set will be open. And it'll be a union of connected components. And how many connected components will there be? Well, there's on the order of e to the d of them at most. That's not special to this polynomial. That's a general theorem due to Milner and Thom. But what is special is that each one of these cells, these open connected components of the complement of z of p, is only going to meet a fairly small number of curves from my collection. So each curve presumably will pass through several cells, maybe about e of them on average, but no one cell sees too many of these curves. So at most, the number of curves divided by e to the d minus 1, that's an upper bound for the number of curves that intersect any given cell. So in some sense, the curves are evenly spread around amongst the various cells. And so this version for curves was proved by Guth. A version for points was proved by Guth and Katz. And indeed, the version for points is enough for what we're doing, but it's a little bit cleaner to discuss it for curves. So this theorem of Guth and Katz we're going to use to prove the lemma on the top right board. And we're going to prove the lemma on the top right board by induction on the size of f hat, so on the number of curves. So we're fixing a case where mu is about 1. We fix epsilon. We want to prove this result by induction. And so I won't talk too much about the base case. The interesting situation is the induction step. So everything lives in Rk plus 1. So I'm going to be, so D is Rk plus 1. That's the dimension of the Euclidean space where this problem takes place. And I'm going to partition Rk plus 1 into some number of cells. I'm going to use a polynomial of degree E. There's going to be roughly e to the k plus 1 cells. E is a number I'm going to choose later. And how many curves intersect each cell? Well, it's roughly the total number of curves divided by e to the k, right? It's the e to the power of dimension minus 1. Not sure why it's doing that. And what do I want to say? So look at each one of the prisms, so these are these sets R hat, these are these prisms in k plus 1 dimensional Euclidean space, and these are connected, and the cells are connected. So what does that mean? It means that either, if I take a prism, either it intersects Z of P, or if it doesn't intersect Z of P, then it's contained entirely inside of one of the cells, right? Because the cells are these open connected sets. The prism is connected, so it just follows from connectivity. So for any given prism, either item I happens or item double I happens. Not sure why it's not letting me switch slides. There we are. So this is an idea which, well, as best I'm aware, it first appeared in a paper by Larry Guth, where he was using polynomial partitioning and the polynomial method to improve estimates on the restriction conjecture in 3 dimensions. And he also used this sort of induction idea and using polynomial partitioning to divide the problem into smaller sub-problems. He wasn't considering prisms, he was considering something called wave packets, but that's okay. So we can divide our problem into 2 scenarios. So we say that we're in the cellular case if at least half of the prisms are contained inside of a cell. So item 2 occurs for at least half the prisms. And we say we're in the algebraic case if that doesn't happen. So item 1 occurs for at least half the prisms. And for those of you that are experts in this kind of problem, you might not be surprised to know that the cellular case is this straightforward situation. So imagine we're in the cellular case. At least half the prisms are contained inside of one cell. The prisms are probably spread around amongst various cells, but each prism, or at least half the prisms, each one of them is just in one cell. And so I'm going to apply the induction hypothesis, because this is a proof by induction, inside of each cell. So how many curves were there inside of any given cell? There's about the size of f over e to the k. The induction hypothesis says there's about the size of f over e to the k to the power of k plus 1 over k plus epsilon. That's the number of prisms that could be inside of that cell. And we can simplify that. And so that's how many prisms on the upper right board are inside of any given cell. It's an upper bound. How many cells are there? There's at most e to the k plus 1 cells. All of this, there's some constants floating around, but that's okay. And so when you add up our bound on the number of prisms inside each cell times the number of cells, we get exactly what we want. We get the size of f to the k plus 1 over k plus epsilon. And we even get a little gain, this e to the negative epsilon. And that's good because this big O is hiding some implicit constants, which depend on the degree of the curves, which is going to be some very small power of delta. And so we select E big enough to be able to counteract those gains from these powers of delta, which are suppressed in this problem. So we select E fairly large, E to the negative epsilon, thus is fairly small, and this makes the induction close. So we've got the desired bound on the number of these prisms in the script R. So if we're in the cellular case, everything works. It's just a proof by induction. And these ideas aren't really new. They've been floating around for maybe 10 years or so. What is often the case for these kinds of problems is the cellular case is fairly straightforward, and the algebraic case is often not straightforward. It sometimes requires new ideas. And so most of the new ideas come into play here in the algebraic case. So let's imagine we're in the algebraic case, and let's analyze what happens. So what does it? So if if item 1 occurs, so if you have a tangency prism R hat and it intersects the boundary Z of P of this polynomial, then what does this mean? It means that R hat is contained in a slightly thickened neighborhood of the boundary, say the delta to the 1 over k neighborhood of the boundary, because delta to the 1 over k is a bound for the diameter of each one of these prisms R hat. Okay, so let's imagine that's happening. And I'm going to make a few additional assumptions. And at the end, I'll discuss how we can remove these assumptions. But let's imagine, so each of these functions f hat, its graph is a space curve in Rk plus 1. And let's imagine for the moment that these space curves are actually also contained in the thickened neighborhood of Z of P. So what we know is that the prisms are contained in the thickened neighborhood. And we're interested in a situation where these space curves are interacting a lot with the prisms. So it's not such a stretch to imagine that if the prisms are in W or the thickened neighborhood of ZP and a curve interacts with them a bunch, then the curves are also inside this thickened neighborhood. Turns out we can reduce to that case, but for now, we'll just assume it. And the second item, item B, is a little bit more subtle. So in general, Z of P is a variety in RK plus 1. So it's this codimension 1 variety. And usually a variety you can't write as the graph of a function. But let's just imagine for the moment that this variety could be written as the graph of a function from Rk to R. And not only that, of a Lipschitz function. So that's kind of a lot to ask. But let's just imagine for the moment that that was true. If these items A and B were true, then there's a rather interesting consequence. So we're asking that the graph of f hat be contained in the thickened neighborhood of Z of P. What is the graph of f hat? Well, it's points of the form t, comma f of t, comma f prime of t, all the way up to f to the k minus 1 of t. So for every time in the interval I, this is contained in the thickened neighborhood of W. So that's what assumption A is saying. And assumption B is saying the thickened neighborhood of Z of P is this Lipschitz graph, right? It's the set of points in Rk plus 1, so that the final coordinate is almost given by the Lipschitz function of the previous coordinates, right? The difference between the final coordinate, xk plus 1, and this Lipschitz function is at most delta to the 1 over k. So what's the consequence if both of these things are simultaneously true? It says that a ordinary differential equation is satisfied, or almost satisfied, right? It's saying that the k plus first derivative of f at time t is a Lipschitz function of the time and the previous derivatives up to some error, delta to the 1 over k. And that's an interesting situation, right? It's saying that all of my functions satisfy the same ODE up to small error. And we're interested in a situation where you have rectangles or tangency prisms that are rich. So that means that you have a tangency prism and many functions are all incident to it. So let's say I have two functions, two lifts, f hat and g hat, and they're both incident to the same tangency rectangle R. So at the moment, every function satisfies this approximate ODE on the upper left board. And to be tangent to a common rectangle means that they satisfy the same initial value problem, because at a point in that rectangle, the functions agree up to a certain accuracy, and their derivatives agree, and their second derivatives agree, and so on and so forth, all the way up to their k minus, in fact, even all the way to their k minus first derivatives, but certainly to their k minus second derivatives. So that's exactly what an initial value problem is. So we're saying that the two different functions, f and g, satisfy the same initial value problem, or up to small error. And so some version of Gronwall's inequality says if two functions almost satisfy the same initial value problem, then they have to remain rather close for all time. So this is this bottom left implication that f and g are going to have to agree with each other on more or less this entire interval up to some error, delta to the 1 over k. So that's kind of interesting because I took just two different functions, f hat and g hat, that were incident to the same rectangle r hat, and I concluded that they have to stay close to each other for all time. So what does that mean? It means look at all the functions that are incident to r hat. All those functions have to stay close to each other for all time. But if you remember when I drew that picture of what it means for a rectangle to be narrow, well, I was a little bit vague because I only drew a picture, but what was happening in that picture was I had a whole bunch of functions all tangent to this same rectangle R, and they remained close to each other after they left R for pretty much the entire time interval. So if the situation is happening that's being discussed on the bottom left board, it means that this rectangle R is narrow, it's not broad. And that's not allowed because the whole point is I'm interested in this set R tilde, or R hat rather, of broad rectangles. And I've just concluded that if I'm in the algebraic case and these items A and B are true, then my rectangle fails to be broad. So that's a contradiction. And what this is saying is, at least up to these assumptions, capital A and capital B on the bottom right board, this algebraic case really isn't an enemy at all. It can never happen. So let's talk a little bit about assumption A and assumption B, because they seem rather stringent. Turns out assumption A is not too bad. And it's because, as I was suggesting before, if all of your tangency prisms are contained in the thickened neighborhood of Z of P, and you're interested in functions that interact a lot with these tangency prisms, then it might not be true that the graph of each f hat is contained in this thickened neighborhood, but the graph will intersect this thickened neighborhood over fairly long intervals. And you can pick whichever interval is most important and do that for every f hat. And then after some pigeonholing, you can say that, well, for each function, there's some interval, and the lengths of these intervals are roughly the same for each one of these functions. And this is where all the interesting action is happening. And you can rescale things so that those intervals become unit length and break the problem into subproblems. So this is sometimes called a two ends reduction and a rescaling. And this can be made to work. So you end up with a new problem. It's not the original problem. It's not the original set W. It's a new set W. But that's okay. You sort of zoom in on an appropriate part of your problem. And now you're in a situation where assumption A will hold. Assumption B is a little bit harder. In general, you really don't expect an algebraic variety to look like the graph of a Lipschitz function. You don't even necessarily expect the thin neighborhood of an algebraic variety to look like the thin neighborhood of a graph of a Lipschitz function, right? That second statement's a bit easier, but even still, it's a lot to ask for. But something is true. So it's the following, let's call it a proposition. So first of all, everything here is taking place in a compact setting. So you could imagine that we live in Rn you could imagine you live in the n-dimensional cube, maybe n equals k plus 1, but later we'll have to consider other values of n. And let's say we have a semi-algebraic set. So you can imagine the thickened neighborhood of z of p, and it has small volume. So in this initial setting, I have the delta to the 1 over k neighborhood of z of p. So that will have volume roughly delta to the 1 over k. It'll depend on the degree of p, but in a fairly mild way. So if I have a semi-algebraic set of small volume, then I can break it into two pieces, where the first piece is the thin neighborhood of a Lipschitz graph, which is exactly what I want. So that was what assumption B was saying. And the second piece projects to one lower dimensional space. That projection will always be semi-algebraic. That's the Tarski-Siedenberg theorem. But what's not so obvious is this projection will have small n-1 dimensional volume. So I can always break a semi-algebraic set into two pieces in this way. And then you can just repeat. You can take the set W2, apply this proposition to it. It's now written as a Lipschitz graph plus a piece whose projection to Rn-2 is small, and so on and so forth. And the whole point is that once you project down a dimension, you still have a ODE, like on the left side. It's just an ODE where instead of controlling the k minus first derivative, you control the k minus second derivative, and then the k minus third derivative, so on and so forth. So the directions in which you project are very important. They have to correspond to directions that obey the geometry of the graph of f hat. But if you do that, then everything works without any problem. So that's a way to reduce to the situation where assumption B holds. You have a Lipschitz graph. Unfortunately, the Lipschitz constant can be a bit large, so you have to control that carefully. And so everything I've said here, there's certain quantitative dependencies that you have to be a little bit careful about. But all of this can be made to work. And this allows you to handle the algebraic case. So that's all I wanted to say about the proof. I'll just briefly summarize. So we have this collection of geometric maximal functions, and we're trying to understand their operator norm bounds from LP to LP. And we can look at an adjoint problem where we have a sum of characteristic functions of thickened curves. We're trying to understand the LP norm of such a sum. And the main enemy occurs from these types of clamshell configurations where you have many curves that are all mutually tangent, potentially to fairly high order at a common point. And this is occurring at several different locations. And the way to show that such situations can't happen are through these sorts of tangency or discretized incidence results, saying that if you have a collection of curves, the number of tangency rectangles they determine can't be too large. And to prove that, we use these lifting techniques, which then will bring the power of polynomial partitioning to bear. And that brings us to a situation where we have to analyze the algebraic case. And there we can be using tools from real algebraic geometry to understand what's going on. Okay, so I'll finish with that. So thank you very much.
Any questions, anyone? Has anyone from the online audiences has any question?
Yes, can I ask a question?
Yes, please go ahead. Please go ahead.
Do you construct approximate identities in algebras or ideals under convolution?
I do not do that, no.
Because, you know, usually when you take one norm, P norm, and these things, then you construct Siegel algebras of functions, you know, instead of the convolution, you know, within the setup, you take convolution with elements in L1 of elements in L1 intersection LP, and then L1 intersection LP becomes Siegel algebras under different norm. And so there are approximate identities which are bounded for L1, but for L1 intersection LP, there are approximate identities which are not bounded. So since you are taking approximations, you might even have approximate identities in algebraic setup, where product or convolution is also considered. That is my one question, whether with all these inequalities, you construct Siegel algebras or not, and then approximate identities in that or not. That is my one question. And second is what I wrote in the chat. You know, Jürgen Preston and Kathy Sellish have a paper where they say that Schauder decomposition will have some restriction on the degrees. You cannot have nth member of nth degree. The degree is larger than n, like bigger than 3/2n or something. So when you took polynomial approximation, do you keep a record on the degrees or not? And this paper by Preston and Sellish is a good example, you know, because that tells you that you cannot have arbitrary degree Schauder basis, you know, there is some restriction lower bound on the nth term in a Schauder basis. Okay. So, and Jürgen Preston, Kathy Sellish, H.N. Masker, you know, they have a lot of polynomial approximations. And wonderful talk. Thank you very much. Thank you.
Thank you. Maybe I'll start with your second question. So in my setting, we are able to approximate functions by polynomials of relatively low degree in part. So I see this reference you sent me. One of the keywords is detection of singularities. I haven't looked at this paper, but I'll mention that these functions are all C infinity, and we have quantitative control on all their smoothness norms. So it's possible that this is what allows for fairly low degree polynomial approximation. I mean, the degree of these polynomials is going to depend on the CK norms, but the CK norms are all going to be fairly under control. With regard to your first question, one way of thinking about everything I've said is it's true that I'm proving LP to LP bounds, but everything I've said remains true if you just restrict, say, to Schwartz class or any other collection of well-behaved functions. And in fact, for everything I'm doing, you could restrict your attention to Schwartz class, but all the bounds I'm describing from LP to LP, the operator norm is only allowed to depend on the LP norm of my function, not on any of the other, say, Schwartz semi-norms or anything like that. So I claim that if you can do this for Schwartz functions with an LP norm that only depends, with a bound that only depends on the LP norm of your Schwartz function, then we can recover the result for general LP functions as well. So you were describing LP intersect L1, so certainly that is a nice subclass, but I claim I can just restrict to Schwartz, which is probably an even nicer subclass, and everything I've said goes through in that setting as well. Yeah, those were good questions, so thank you.
Thank you very much.
Yeah, I just wanted to ask, so are you using the curvature of the curves in any place here in your setting?
So what's important is I need control over how tangent curves are allowed to be. So there are problems like the restriction conjecture where curvature is playing a rather essential role. You can look at flat manifolds and they're not going to have the same sort of restriction mapping properties. Here, curvature is not playing an essential role in the same way. But what is important is that I control how tangent distinct curves can be. So lines, which distinct lines can't be tangent at all, they can intersect, but the moment two lines are tangent, they agree. That's the best situation. You have the best LP bounds in that setting. So in some sense, curvature is more of an enemy than a friend, in contrast to, say, the restriction problem.
Okay, and what about LP to LQ bounds? Here you are studying LP to LP bounds.
Yeah, so that's a very good question. And the short answer is I don't know how to prove LP to LQ bounds. It's not even obvious to me what the correct answer should be for the Bourgain circular maximal function. That's one of the few settings where we actually have a fairly well understood theory of which LP to LQ bounds hold. And this is a result of Schlag. And for pretty much any other maximal function, I don't think it's known. And the techniques I've discussed, I'm not aware of how they could be used to prove interesting LP to LQ bounds, although it's possible. So yeah, that's a very interesting question. I don't have much to add.
Okay, thank you.
Okay, hi, Josh. Thanks for the talk. I wonder if there is similar estimate for narrow rectangles, or if that can be, if such an estimate can be avoided by using different tools.
Well, we have to be a little bit careful because one situation that could occur is imagine that all your functions are almost identical. So each function is just an infinitesimal perturbation of the others. So their graphs at scale delta coincide. So this, at least at the level of generality that I stated in my theorem, that is allowed. And if that were to happen, then you could cover that common graph by a bunch of rectangles of length delta to the 1 over k and width delta. And there'd be quite a few of them. There'd be 1 divided by delta to the 1 over k of those rectangles. And they'd all be extremely rich. Their richness would be the same as the cardinality of the set F. So that would very much be a counterexample to the theorem that I wrote if you removed this restriction that the rectangles are broad. So for narrow rectangles, maybe what you could do is you could try to make them longer. You could try to find the correct length so that maybe this longer rectangle is sort of the correctly capturing the geometry of the functions that are tangent to it. And any longer rectangle, if you were to try to make a longer rectangle, the functions would begin to diverge once they leave that longer rectangle. So there will be an analog of the theorem I wrote for that. But if you just want rectangles of dimensions delta times delta to the 1 over k, and you don't ask that they be broad, it's not obvious to me how to say anything interesting because of this example I described to you, which is a major enemy. I mean, it's a counterexample to any hope of any kind of theorem controlling narrow rectangles. I'll maybe follow up though by saying that the reason for creating this definition of broad rectangles is that broad rectangles, if you pick the correct scale, really are capturing the geometry of what's happening with the graphs of these functions. So if you understand broad rectangles and you're willing to do that at every possible scale, then you can really understand what's happening with L. And so that's enough.
Okay, thank you.
So does anyone have any question? Oh, okay, so in that case, there is one more message in the chat. Joshua, could you please check?
Yes, I put that message in chat. Paul Bankston studied topologically, curves and approximations. That might be interesting. It's old work. And he was a student of Donna Strauss.
Thank you. I'll take a look at that.
Okay, I think we can stop here. Also, thank you very much for the wonderful talk. You have a good day.
Thank you. Thank you very much for having me. It was fun giving this.